Here is a gate problem from Instrumentation Engineering from the year 2022, and this is from the Digital Electronics module. But judging by the analysis of this problem, it is more or less something that has got to do with the basic understanding of circuit theory, and more predominantly, it has got to do with our understanding of Thevenin's theorem. So here is the question. A resistor ladder DAC receives a digital input that results in the circuit having the state as shown in the figure. For this digital input, the Thevenin voltage VTH and Thevenin resistance RTH as seen at the output node are dash and dash. So here are the options. This is a MCQ type question. So VTH is equal to 0.5 volt and R Thevenin is 1 kilo ohm. Second option is 0.5 volt and 2 kilo ohm. Third option is 1 volt and 1 kilo ohm. And fourth option is 1 volt and 2 kilo ohms. And this is the typical circuit of a digital to analog converter. So the point to note here is that this is an R2R ladder type network, given the fact that this R is equal to 1 kilo ohm and then 2R is equal to 2 kilo ohms. And these are the three switches. So this is basically a 3-bit converter. And it is also seen that the switch A is connected to ground, switch B is connected to plus 4 volts, and switch C is again connected to ground. And therefore we can claim that logic level 0 is equal to 0 volts, and logic level 1, this is equivalent to 4 volts. So we have to proceed with how to solve for the Thevenin voltage and the Thevenin resistance when this is the output node. So basically we will look at this circuit, we will look at this entire circuit from this output node. So looking at this circuit implies that it's as if I am sitting here with my eye and I'm looking into this part of the circuit, and therefore the Thevenin voltage will be the open circuit voltage between this node and ground, and the Thevenin resistance will be the resistance of this network with all the independent sources deactivated. So let's go about. So here is how to approach this question. Let's first solve for the Thevenin resistance RTH, and what we can do is we can, with switch A we can connect it to ground, with switch C we can also connect it to ground, and then with switch B we directly connect it to this 4-volt source. And therefore our objective is to find out the resistance looking from this output node. So the first stuff to do is to deactivate this 4-volt source. Because this is a voltage source, we have to replace it with 0 volts, and basically this then ends up getting terminated to ground, and there are no dependent sources. So all we have to do is to solve for this resistive network, and it is easy to see that this is just a connection of resistances which are in either series or in parallel. So it's a series parallel resistive circuit, and in fact not even an engineering problem. This is more or less a 12th standard question. So we can start with this part of the network and then find that this 2 kilo ohm and this 2 kilo ohm, these are in parallel, so they form a 1 kilo ohm resistance. And then you have a 1 kilo ohm over here, so this is the equivalent 1 kilo ohm. So I have 1 kilo ohm and then another 1 kilo ohm, so this becomes 1 plus 1 equal to 2 kilo ohms because these are in series, and therefore you have 2 kilo ohms for this combination. Then you have 2 kilo ohm. Looking from this node towards the left hand side, I find 2 kilo ohms, and then that 2 kilo ohms and this 2 kilo ohm, they become a parallel network, and this equivalent resistance becomes 1 kilo ohm. So the resistance looking from this part of the network, so if you follow this circle, so this is forming the equivalent 1 kilo ohm, and then I have a 1 kilo ohm in series with another 1 kilo ohm, so that becomes 2 kilo ohms. So looking from this part of the network, this is the the big circumference. So this one is equal to 2 kilo ohms. And then finally you have 2 kilo ohm and 2 kilo ohm which is in parallel, resulting in R Thevenin being equal to 1 kilo ohm. So the Thevenin equivalent resistance is equal to 1 kilo ohm for this DAC circuit. Now looking at the Thevenin equivalent voltage, this is also called as open circuit voltage, and therefore what is the voltage that I find looking from this part of the network? So this is one node and then the other node is ground. So what is the equivalent voltage that I find? That is the Thevenin equivalent voltage, also called as open circuit voltage or Thevenin's open circuit voltage. So how do you do it? You have 2 kilo ohms from this part of the network. So this is the equivalent 2 kilo ohms. I have 2 kilo ohm here along with that 4-volt source. So basically this one is an equivalent 2 kilo ohms. And over on the right hand side, we have this resistance which is 1 kilo ohm. So I'm talking about this resistance which is 1 kilo ohm. And then there is another 2 kilo ohm resistance. So this is the 1 kilo ohm resistance along with a 2 kilo ohm resistance. And we can use lot of methods to find it out, but the one that I have used here is basically the nodal method. So just consider that the voltage at this node is unknown, and let's call it as small v. And therefore we can consider that, let's say some current is flowing from bottom to top through this 2 kilo ohm resistance, and then it can go to left side as well as through the right side branches. And therefore we can frame the nodal expression as 4 volt minus of small v divided by 2 kilo ohms must be equal to small v minus of 0 divided by 2 kilo ohms plus small v minus of 0 divided by 1 kilo ohm plus 2 kilo ohm. And from here, if we do this little math, we find that I, this current I is equal to 0.5 milliampere. And therefore, the open circuit voltage of the Thevenin's equivalent voltage is simply the multiplication of this current, small I, multiplied by the 2 kilo ohm resistance, and this becomes equal to 1 volt. So the Thevenin's voltage is equal to 1 volt and the Thevenin's resistance is equal to 1 kilo ohms.